It's Reefer Madness, the podcast, with Trevor and Kirk.
Kirk, we're back.
Hey, Trevor. How's it going?
Good. So for the illusion, you keep putting this on YouTube, I have a slightly different colored shirt on than I did 5 minutes ago, so this is a completely new episode.
True. I left Northgate on. Got my Northgate. I'm advertising. Elbows up. I'm advertising for the Northgate bike trails in Dauphin, Manitoba, Canada. If you ride mountain bike and you want some elevation and about 45 kilometers of wilderness trail, come to Dauphin, Manitoba, Canada, and bike ride at Northgate. A little plug for our community.
Sort of related. A son of a friend of mine trains at Northgate. He's 16, 17, and their team just recently went out to Canmore, Alberta to race with the big boys, and he won a time trial or two. So, apparently you can take a prairie kid, throw them on Northgate, and turn them into a Canadian class athlete.
Bike rider.
But not a mountain biking episode. But I'm going to start on a digression. Radiolab. When our podcast grows up, I want it to turn into Radiolab. Radiolab, I think, is still my favorite podcast out there. They do lots of sciencey stories. It's surprising but it was started by Jad Abumrad. It does lots of really cool audio stuff, but they do a lot of science episodes. And one of my favorites ties in nicely to this. So the title of their episode is The Dirty Drug and the Ice Cream Tub, which is just a great title. And it is about the discovery of rhabdomycin, which was discovered by a scientist who spent some time in Canada, found on Easter Island, or as the local inhabitants, Rapa Nui. So that's why the rapamycin. And rapamycin is one of these things, it's got some legitimate uses as a drug, but more and more people are talking about it being just, the cure-all for everything, including just aging. So, and which may or may not be true, but it was just going, and we're going to touch on that a little bit in this paper, but the fact that our guest started doing some anti-aging research and then did some cannabinoid research, and they found the two go together. And we talk a little bit about rapamycin. I had to mention a Radiolab episode. So right after this, go and listen to The Dirty Drug and the Ice Cream Tub, and you can hear about how a podcast should really be done and the origins of rapamycin. And now I'm going to come back to our guest. So today we've got Dr. Andras Bilkei-Gorzo, and he says his name much better than I do. He's a researcher at a German university, but he's originally from Hungary. And our producer, Renee, said, hey, there's this thing about cannabis and anti-aging mice. That sounds interesting. And we got him.
Yeah. No, you're talking about mTOR, right? When you went on about rapamycin. Yeah. Well, and mTOR all has to do with the endocannabinoid system and how the endocannabinoid system actually has an effect and touches on aging. So this is a really interesting study. It's one of your heady episodes. The study out of Bonn University, they did it in conjunction with the Hebrew University at Israel, which is where Raphael Mechoulam came from. Mechoulam. Yes. That's where he came from. So there's a definite link to the root of cannabinoid research. I enjoyed reading the summary, and the paper was really dense for me. It's a classic paper for pharmacists and those science guys, but I found it very interesting. The restoration of the CB1 signaling on old people. You can actually maybe make us younger by using cannabis, but I may be jumping ahead here.
No, that's and also listen. You damn youngers out there, depending on how young that is. We talked about a previous episode how elderly keeps moving in my mind, but there is even some, and in mice, not people, but when they gave doses to the young mice, their brains started looking a little bit like old people, and they gave them the old mice, and they started looking like young mice. So I thought that was interesting that, maybe us slightly older people have more reason to use cannabis than the young bucks out there.
Yeah, and maybe for the non-sciencey type, mTOR, the mechanism of it targets the rapamycin, so help me with that.
It's where rapamycin binds onto.
Right. So it's the central hub of cell growth and metabolism, right? So this is where our cells age, is in this area, and the endocannabinoid system affects it.
Yeah, and Andras explains it better than we are, but yeah, we've known for a long time that if you starve things like little worms and stuff, if you starve them, don't starve them till they die, but don't give them quite enough food, they actually live longer. Like these tiny little worms and dishes, they've made them live 2 and 3 and 4 times as long as they normally do by giving them slightly less calories. And they've done that with all sorts of different beings. And there's people who argue that, if us humans ate less, again, not starving, but ate less, we might live longer. And kind of the idea being, if your body thinks there's not enough food, because it isn't, it slows down, and i.e. slows down, doesn't age as fast. And one of the things rapamycin might do is kind of trick your body, even if there's enough food around, to think it's starving, and thus slow down the aging process. And again, Andras will get into this better, but one of the fascinating things about the low-dose THC is it might do 2 things. It might tell like your fat cells to slow down, but keep your brain cells working at full speed, because normally if the mTOR goes off, that rapamycin signal goes off in your brain cells, it tells them to slow down too, and that makes them be dumber, like not produce enough protein to do their thing. So if that's this bi-directional parts. But anyway, we're getting ahead of the guest.
Well, let's listen to him.
Okay.
So
okay.
Hi, this is Andras Bilkei-Gorzo. Indeed, I'm from Germany, from the University of Bonn. But to tell the truth, I'm Hungarian, working since 25 years almost here in the University of Bonn. And I had 2 major fields. One is the cannabinoid system, and the other is aging, so the biology of aging. And during my studies, it just happened that these seemingly separate fields, I learned that they are interconnected with a lot of, I would say, branches.
And that's fascinating, and that's how our producers stumbled upon your study. And for another German connection, he actually grew up in Hamburg, so we've got a few German connections on this. So and we'll post links to this, but we're going to talk about sort of 2 different studies that Andras' team has done. But we're going to start with a 2017 one. Chronic low dose THC restores cognitive functions in old mice. Now, the first, and I'm a pharmacist, so I'm just always amazed by this. And we've talked to other researchers who look at mice, and one of them called mice just livers on legs. Low dose in a mouse, 3 milligrams per kilogram. So, if you had a 100 kilogram person, that'd be 300 milligrams. That'd be a huge dose in a person. But in a mouse, that's a low dose?
Yeah, it would be an extreme dose for a human being. So if you calculate indeed, it's much of the usual dose that one would use for medical purposes, I would say. Come on, if you compare the human brain and the mouse brain, and even if you consider that they contain more or less the same amount of CB1 cannabinoid receptors, or receptors that bind cannabis in the brain, more or less in the same distribution. But compared to the mouse body, the mouse brain, and the human body to the human brain. So the point is that rodents generally are much less sensitive to psychoactive substances, to any psychoactive substances.
Okay.
So this 3 milligram per kilogram in a mouse do not induce any, but absolutely any physiological effect.
Wow. That's interesting. And that's why, we have to, studying mice are interesting. And like you said, you can study a young mouse is 2 months old and an old mouse is 18 months old. So that makes it much more convenient. But we have to remember mice aren't people. Okay. So, in this first one, we had young 2 months, mature 12 months, and old 18 months old mice. And you gave them placebos or low dose THC, and then you checked to see how their mental facilities were doing with something called Morse water maze test. So maybe just tell everybody what that is.
So for human beings, it's relatively easy to test whether they learn something or not. We can just ask. No? They have to solve tests, fill out a form, or make any task. It's easy. For animals who cannot communicate so well, it's not as easy. So usually we say that learning is something that the animal change their behavior in an adaptive way so that they have a better outcome after doing this behavioral change. So it's very easy to say that this Morse water maze test, we put the animal to a pool filled with water. And mice not only can swim, they can even float on the water. So unlike human, they just remain floating in the water, but they really hate it. So they do everything to get out from this wet environment, like water maze. So usually in this test, we put an escape platform under the water. But from the angle the mouse swims, cannot see the platform. So at first it just swim random up and down, try to escape, and only by chance find the platform. And it's happy, it take out, dry the animal, and after 5 minutes, I have to admit, I put it back.
Okay.
And then again, the mouse is paining, swim everywhere, find the platform, and be repeated after the repetitions. Then it will just learn the position of the otherwise invisible platform. It's invisible for them again.
Okay.
And we just measure the time the animal spent from start to find the platform.
Okay.
And obviously, when the animal learns, it will be shorter and shorter and shorter. And after a while, we put the animal to the water, swims directly to the platform, and it's over. So sometimes it's like 4 seconds they finish the test, and then they learn the position of the platform. So in this way, when we measure the time the animal needs to find the platform individually and compare these times between the groups, we can just learn that which learn better. Better means that they learn quicker. Where is the platform?
Okay, and not surprisingly to all of us getting a little bit older, without THC, you found that the young mice find the platform faster than the old mice, right?
Yeah, it was somehow expected. I have to admit, I checked in the literature, and it was 100 times checked in this particular animal line that this particular age learns slower. Otherwise, good for us and good for the animal. It depends on the behavioral test or learning test we use. So sometimes we see this age-related decline very early, lying in the social recognition test, or later, so that they can maintain their learning ability up to the longer age. But there are some modalities, I would say, learning forms that they just lose relatively quickly.
Okay, and so now this leads into you putting little pumps on the mice for putting in either a placebo or a low-dose THC?
Yeah, exactly. So the very background from the whole study, we had like 2 findings before. I have to tell probably in the beginning we started. They were really boring descriptive tests, but we found that also the cannabinoid system activity in our body, because probably not everybody knows, but our very body can produce cannabinoid, the so-called endocannabinoid. It binds to the cannabinoid receptor that has very important functions, for example, maintaining our psychical abilities, which is a very important function. And surprisingly, despite of this important function, the activity of this cannabinoid system declines in aging. So the older the animal or the older the human being, it's less active.
Okay.
That was one pillar, that in aging, the cannabinoid system activity goes down. The other pillar was that we tested knockout animals. They are genetically modified animals where one gene is missing. Case, that was the cannabinoid receptor 1, the very receptor that is responsible for the THC effects in the brain.
Right.
And when this receptor was missing from the animals, they showed an accelerated brain aging.
Okay.
So they were very good, absolutely good in young age. You cannot distinguish wild type and knockout animals, but when they got older, they became worse and worse in different learning tests. And we interpreted that they had an accelerated brain aging. So here came the idea that if the cannabinoid system activity declines in aging, and we do know that low cannabinoid system activity, or in this case, no cannabinoid system activity, accelerates brain aging, what happens if we increase the receptor activity, the cannabinoid system activity, in young and old animals? Because obviously, if we give the very same treatment to young animals, we overdrive a normally functioning system.
Okay.
If we give the very same treatment to old animals, then we restore practically the activity of the system to the original level.
Okay. So that was all sort of things you sort of knew before we started this test, right? This was kind
Exactly.
of okay.
Exactly. They were the two starting points.
Okay. So it's you did this test and a few other cognitive tests to these mice, and you found the low dose THC, like you were saying, basically made the older mice be able to do these cognitive tasks similarly to the younger mice. And
Exactly.
when the placebo went in, that's not what happened.
They never became super animal or very wise animal. Never ever.
Okay.
But they could return their learning ability or memories to the level that was typical to the young ones.
Okay. And then you sort of got into the how or the why, and now we'll try to get you to explain some slightly more complicated things simply for us. But everybody's heard of DNA. It's in the middle of all of our cells, and DNA is usually bound up with something called histones, and that makes a tightly packed little structure called chromatin. And something about the histones getting acetylated opens it up a little bit to let things in there to get the information out of the DNA. We call it an epigenetic effect. Do you want to talk a little bit about that and what we think the THC was doing to open up that epigenetic bundle a little bit?
Exactly. So there's a lot of speculation. What happens with our cells during aging? Because the genes are more or less the same. So if there is no major mutation in an animal and a human being, the genetic composition is absolutely the same in a baby, in a middle-aged person, and in the very old one. The genes are the same. So that is why logical that the regulations of how these genes express, how they act, differs. And what that we found that also in each cell there is all the information that necessary to make up a human body in a human cell. The cell that is in your skin makes only skin. The cell is in your brain makes only neuron, and so on and so on. So also all the information is there, but they use only a very, very small percentage of this huge amount of information. And indeed, the so-called histones that govern that which genes allowed to express and which genes not. And it's very well functioning in young individuals. And we do know that in younger ages, the strict control is disrupted. Very simple explanation for the cancer. The cancer is a normal human cell that forgets that it should be like a blood cell producing cell or a skin cell or whatsoever, but turns back to the embryonic stage. And that here also in most of the cases, there is histone deficit in the background. And it's not so bad, but also in the brain, where usually the neurons do not go cancerous under normal circumstances, there is also a change in this histonic regulation. So again, this original strict control will be, I would say, loosened. So genes that they shouldn't be expressed will be expressed, and genes that should be expressed are not expressed as well. In the mouse brain, the second is very typically associated with increasing age. So more and more genes will be blocked. But usually they should be expressed, but they are just blocked. And what we found that when we do this low-dose long-term treatment, practically this blockade will be erased, and the gene expression in THC-treated old animals is very, very similar than in the control young animals. And maybe a bad message for younger people. What we found that the same treatment in young animals, the THC-treated young animals showed a very similar expression profile like old controls.
Yeah, so I read that. That was very interesting. That you almost had the opposite effect when you gave the THC to the younger animals.
Absolutely.
Did I get that right?
So practically we can so briefly summarize that the THC treatment, at least in this expression level, made the young brain old and the old brain young.
Wow. That's really interesting. So, no, that sort of does. Now, you touched on it a little bit with sort of some of the research leading up to this, but let's talk about the CB1 receptor. So you talked about if you had knockout mice were sort of genetically picked to not have CB1 receptors, and then they aged quickly. But you used, and tell me if I've got the terminology right, some mice in one of the trials that had a disrupted CB1 receptor, and initially their learning and memory was better, and then it declined rapidly. Do I have that right? Exactly.
Absolutely. As a young age, they were just brilliant, better than the wild types.
Okay.
For colleagues, I always thought that they are like cars without brake. Really. So if you go to a race without brake on a short term, it will be faster. In the long term, it's not as good.
All right. That is a very nice analogy. Okay. But the interesting part from this, other interesting part for this is when you added low dose THC to these mice with the disrupted CB1 receptor, they didn't get the reversal of the cognitive processes like the mice with regular CB1 receptors, right?
Absolutely. Nothing happened.
Okay, and that just sort of reinforces the thought that CB1 receptor is key to this eventual cascade that affects the histones and affects the epigenetics. That's sort of where that was going.
Yeah, absolutely. In science, it's always how you can prove a mechanism, eh? Because there's always like a chain of events, a logical chain.
Okay.
And, in the childhood, small babies, small kids, how to work something, they just damage it, like break it or stuff like that. So the researchers are like these small kids, just let's break it and let's see what will happen. So that was the logical chain. Let's see whether CB1 receptor is important for this effect. Let's break it, let's delete it, and let's see what happened.
Okay.
So really, we could ruin the effect of THC. So congratulations.
No. And then one of the last lines from your discussion from this first paper, I thought was really interesting. You said other research has shown that blocking histone deacetylation in mice has had shown to be anti-aging, but then when we move to blocking histone deacetylation in humans with disastrous effects, what happened when during the testing of just blocking human histone deacetylation in humans?
Well, the biggest problem with playing around with histone modifications, if you take any compound that modifies that, it will modify in your body, in all the cells. And we shouldn't forget that loosening this expression profile, or loosening the expression, the control of the expression, it can lead to cancer.
Okay.
It's always this big danger. So here the point is that when we treated animals with THC or somebody consumed THC, and it changes also the histone acetylation, let's imagine, but it will do it only exclusively on cells that express CB1 neurons and not in the whole body.
Okay. So that's why. So more specific and with far less side effects, like you said, than if we change histone acetylation everywhere, and that can lead to cancers.
Absolutely, that's true.
So that was my quick run through of the first paper. So now we've the more recent one, the 2024 one, the bidirectional effect of long-term THC treatment on mTOR activity and the metabolome. Now, I have literally never heard of the metabolome before. How about let's start with what's that and what are we looking at?
So when we test the activity of a cell, tissue, or any being, you can do it on different levels. And one level is how the whole biochemical activities, the biochemical networks functioning. And one possibility is like the metabolome analysis, that one measures the level of each possible small molecule. I can technically measure in the cell or in the body and can deduce how the energetic of the cell or the tissue or organ works, whether it's activated or not activated, whether it's prone to diabetes, or it can cover high energy demand, or actively synthesizes lipids like hell, or shouldn't do that. So the metabolome analysis is a very good tool to see what happens actually on the cells in the organism, in the activity, in the biochemical activity level.
Okay, and the other part I've heard of, and maybe other people have, because rapamycin is just a fascinating compound originally found from some fungus on Easter Island, and may or may not be the key to anti-aging everything. So there's lots of interesting stuff in the world about rapamycin and what it may or may not be good for. But tell me a little bit about the mechanistic target of rapamycin, sort of what it does kind of in general.
it's an extremely useful molecule in each cell, because just imagine there are times also in our life when there's scarcity. And there are good periods in life, hopefully, for everybody, but there's plenty of goods. We have plenty of money, plenty of time, whatsoever. So there are times when we have to save energy. There are times we can build, we can travel, we can use it. No? It's good. But the cells is absolutely the same for any animal. No? Just imagine that if there is a scarcity, they shouldn't move a lot, should seek for shelter, and so on and so on. If there is a lot of food, then come on, let's go out, let's eat a lot, and let's multiply. No? This is the typical. And this is true for each cell. So there are times when they had to switch on energy reserve function, and times when they can just thrive, duplicate themselves, synthesize a lot of molecules. And this mTOR is the sensor. Is the sensor if there is enough energy or not enough energy. If there is not enough energy, then it switches to energy reserve and starts anti-aging mechanisms. If there's a lot of energy, then it switches off, and starts, okay, come on, let's synthesize everything. And that is why the rapamycin, it makes a bloody trick. There is plenty of energy in the cells or in the environment, but it tells to the mTOR, it blocks the mTOR activity and says, there is scarcity. Please reserve everything. And it's good. It's generally anti-aging. So if I wouldn't have a look on the negative side effects of rapamycin, it would be good to slow down aging. But it has a really negative effect on the brain. Because for the brain, for the memories, for the formation of memories, for learning, we need again the synthesis of new molecules, new proteins. We need new synapses, connections between the neurons. And if we block it, because of scarcity, then it will impair the learning and memory abilities. And here, the background of this article was that how could it possible that a treatment that has anti-aging effect, and at the same time it improves learning and memory? Because until that point, we thought that they mutually exclusive, so they exclude each other.
Right, and that was one of the many fascinating things about this. So, like you just said, it looks like if you decrease mTOR activity in most of the body, we'll say fat cells, that's good, that's anti-aging, that's fantastic. But if you do the same thing in the brain, it forms less connections, makes less proteins, bad. Memories
makes you dumb. Absolutely.
Makes you dumb, sure. But, and this is sort of where the paper's getting at, how could something maybe do both? Maybe it does different effects on mTOR in the brain as in the body. Is that kind of where the paper was going?
To tell the truth, we had no idea how is it possible to solve this mystery.
Okay.
Because again, it's just exclusive, excluding each other. You cannot have both, but we had it. And that is why we wanted to go on that what on the earth happens in the body, in the metabolome and this mTOR in THC-treated animals.
Okay, so what did you do to our poor little mice friends this time? Were you making them swim and recognize each other, or were you checking out what was going on in their brain and cells sort of after the fact? What did you do to them for this test?
Yeah, so usually learning is always nice, but there's always a big skepsis behind that, because if you say that you take any medicine or compound that binds a receptor, and then it changes this and then that and that, and there's a very, very long chain of events until you get to behavioral change. And usually behind behavioral change can be thousands of factors. That is why in this case, we went even to a lower level, and we checked how the connections between the individual neurons change in treated animals. And and indeed, we could find like a time-dependent change, a time-dependent increase in the concentration of proteins that indicate or show us that how many connections between the neurons exist. So we could really see that in THC-treated animals, a time period long, the concentration of this protein went up, meaning that there's a lot of new formations, a lot of new connections happened in the brain, which is good. That supports the learning and memory abilities.
Okay, so that's the increase in synaptic density.
I didn't want to tell this bloody word.
Well, no. Just if people read the paper, you explained that very, very well. The increase in connections, but another way of saying it is the increase in synaptic density. No, but I think you explained it better. Just in case people read the paper, that's the term that was used in the paper. So tell me more about the bidirectional. What sort of happened in different time frames of the mice being on low dose THC?
No, that is really interesting that when we give THC, we affect the whole body. But seemingly there was a different time scale in the reactivity of the body and different organs. And what we do think that as rapamycin cheated and told mTOR that there is a scarcity.
Mm-hmm.
And that is why it switches on the protective systems. In this case, THC cheated also and told to the neurons are full with CB1 receptors, cannabinoid receptors. Actually, in the brain, the cannabinoid 1 receptor is the so-called G protein coupled receptor is in the far the highest concentration.
Okay.
This is the dominant receptor type in the brain, not in the body. In the other organs, it's moderate low expression, if any. So first the brain reacted, and in the hope that there is a lot of food, they can do whatever they want, they just started to synthesize new molecules, form new connections, so it boosted the learning and memory abilities. But after a while, the whole body had to realize that it was a lie. There is not as much energy, so it's absolutely normal. The animal never ate more. So the feeding, body weight, it just was the same. So that is why after a while, when the body realized, so it's not very conscious, but there are molecular systems that has very good sensors for that, they realized that they run out from energy. That is why then it switched off this mTOR signaling and started this preserving anti-aging activity in the body.
Okay. And just from the paper, 14 days seems to be this magic time period between the body, the brain anyway, thinking that I've got lots of resources, lots of food, and then after 14 days, I was lied to. I better go into scarcity mode. Is that about right?
Yeah. So we had several time points that we measured. We do know that so it's continuous treatment.
Okay.
After 3 days, we do not know that it's before because we don't have day 1, 2. But we do know that after 3 days, the mTOR is very happy and active and thinks that there is a lot of energy. We do know that at day 14, the whole brain is extremely happy and uses this allegedly a lot of energy to synthesize a lot of stuff. And we do know that at day 28, despite of the continuous THC treatment, everything goes back to normal. So at least in that time, at day 28, after 4 weeks, the brain realized that, oops, it's not as it was told.
Okay.
If we focus onto the brain. No?
Right. But you said a different thing is happening in the body, like, for example, in the adipose tissue, because there's no CB1 receptors there.
Absolutely. Absolutely. So in the adipose tissue, the cannabinoid system activity also has a good effect on the adipose tissue. Okay, not so good. Okay, so it increases the adipose tissue. So usually it increases the fat deposits. But here we did say that due to the downregulation and mTOR activity, the adipose tissue started to burn up the fat reserves. It's very typical if somebody has hunger or as in continuously don't get as much energy as needed.
Okay. So, now, a different and a bit of a side thing, but you mentioned in the paper, and I was a little confused. So, low dose THC, and we've talked about this for the two papers, seems to increase things like memory and cognitive function, especially in older mice. But the high dose one seems to impair memory and this mTOR and high dose THC might be involved in why high dose THC causes amnesic-like effects. Can you kind of go over how that all works?
It's not easy to compare these studies because high dose was 50 milligram per kilogram.
Okay.
In one shot. So it was one acute treatment with really high dose. So if you just think about that, at 10 milligram per kilogram, if I treat animal with 10 milligram per kilogram, usually it starts to show signs of analgesia and hypomotility. So they move less. By 20 milligram per kilogram, it's not only obviously hypomotil, but the body temperature also drops down, catalepsy-like symptoms. So 50 milligram is really a good dose. So what I do think that by this high dose, one shot, 50 milligram per kilogram, you can activate totally different network as with a very, very low dose.
Okay.
So it's simply, you can envision that there are cells and receptors, they have different affinities. And if you apply a low dose, you can activate only receptors and cell types that have the highest affinity for that particular substance. If you increase the dose, you will activate more and more receptors and more and more brain areas and regions. So it's absolutely true. If somebody takes a huge amount of THC, suddenly it's very bad for the learning and memory, and it induces amnesia. That's absolutely true.
Okay.
Also, finally, the effect was indirect, but it's fine. That's true.
Nope. Good. Now, towards the end of the paper, you were sort of, the team was sort of thinking about how long we had to give THC, low dose THC, to have these good metabolic effects, and was 28 days the magic number? Was 14 days the magic number? What would happen if someone was on the low dose THC longer, or maybe even chronically? What were you and the team thinking about duration of treatment of low dose THC in mice, at least?
I guess you know something. So it's an ongoing study that I'm just working on. So here is an ongoing study that we treat animals from the age of 12 months, each fourth month, 20 days long with THC. And there's a big colony of animals, male and female, and we continuously test them. It's like health checkup every second, third month. And again, it's ongoing. And we will see how it affects the whole body aging and the life duration of the animals. But I have to tell you that it's high time to start the human studies.
Okay.
Because whatever I find in mice, the first question will be, what does it mean for human life? No? Because even if you
I want to know.
18 months old animals are old. No, you believe me, because I'm the expert, old, but 18 months old, come on, it's for human being, it's a toddler. So it's not easy to compare, even if you say that, a mouse can live like 3 years long, human beings, let's be generous, 120, that 40 times more. But it's not quite true, because like female mice in the age of 12 months, they can't get babies anymore. So it's like
menopause.
So it's not easy to calculate one-to-one, or simply give a factor that how much older they are, how much they age, how quickly they age. So that is why I do think that when we make this kind of speculation about dose, where we say that these animals receive almost 100 times more THC that a human would get. They get older much faster than we humans do that. No? So I do think that we learn a lot from the animal studies, because we have the same cannabinoid receptors. We react in a very similar way to cannabis as mice. That is why I do think that we can interpret the result, that it must act in a similar way in human. But about the dose, the duration, and the critical age when one should start, come on, here we are missing a lot of information. I would say no idea.
Okay. Well, I think those, we're getting close to the end, but those lead to, where I was going was, what do we think humans can learn about this? But how about, before I get to that, if we could give you an enormous bag of money and you could design a human experiment, who would you like to study, and sort of if we had a bunch of human volunteers and a bunch of money to run this, what would you like to know? What kind of study would you like to run in humans if you had a magic wand and we could let you do whatever you want?
Yeah, it would be great to have like a 60 plus probands, and there to do like a health checkup, also for cognitive health checkup every year, like 3-4 years long. And the treatment shouldn't be to have continuous, because we see in this human example that when we started to treat the animals, at least the metabolic changes peaked at day 14, and at day 28 it was just over. So what I do think that in human beings it also would be like although a low dose repeated treatment, but like periods of treatment, like 1 month treatment, 5 months without, 1 month treatment, 5 months without, and also
so like a dose every 6 months or twice a year,
like that.
Okay.
And by the dose we also speculated, because we are blending since years the human study, just never found the support for that somehow. So we plan to add like 3 milligram per day. And 3 milligram is really something that, it depends on the country, but probably you can even drive after this dose.
No, that would, I agree that most places that would be considered a low dose. Um,
Yeah,
so no,
absolutely.
that would be a fascinating study. And then, and I'm sure the answer is, well, we don't know because all the studies have been done in mice, but for your average older person, we'll say your average 60 plus person who may or may not be using cannabis medically for other things, any sort of takeaways for them about what their cannabis use they're using already may or may not be doing for their brains? Do we know anything yet, or is it all still, we need more study?
The usage of cannabis in older age, it's an interesting question because it's used in Alzheimer patients, but only to alleviate some symptoms like aggression or insomnia, like that. There's a very low N number. But for these studies, they did some safety studies. So we do know that under 10 milligram per day per person, the cannabis seems to be safe. That is what we do know. The safety, but nothing else.
So this has been really interesting. I really appreciate you making the time for us and walking through the studies and the tantalizing, everybody's getting older, so everybody's got an interest in, keeping their brain working and staying as young as possible. Did I miss anything? Was there anything else that you think our audiences should know about anti-aging and low-dose THC?
No, I think the major take-home message I want to transmit is that THC acts very differently in young and old individuals. It's one point. The second, that in young individuals, other than fun, I don't think that there's medically too much positive effects. No, I was nice. I think it's rather negative. But in older age, the very same treatment seems to be positive. So I would encourage older person, again with low dose, it's 3 milligram, maybe disappointing, but it doesn't have psychoactive effect. But really it's something that could save our good memory for a longer term.
Andras, this has been a fantastic and interesting study. Thank you very much.
You're welcome.
Okay, so just stay on the line for a second as there was really two studies there. The first one, they did mean things like made mice swim through tanks and try to find the invisible platform to get dry, and not surprisingly, if you make them do it 2 or 3 or 4 times and time them how long it takes them to find the invisible little platform, the younger mice did better than the older mice. But if you gave them a low dose THC, the older mice now found the platform on repetition as fast as the younger mice. So that was cool. And that was sort of along the lines of your endocannabinoid system gets older and then you perform, and then your CB1 receptors seem to go away. And having a little bit of low dose THC seems to make them not, quote unquote, go away. And then the second one was the really interesting part. That was the bidirectional, make your brain think it's got lots of food and make your body think it's not got lots of food. So your brain keeps being smart and your body keeps anti-aging. Well, that's my real brief summary.
Yeah, no, that's good. I always try to bring this stuff so that I can apply it in clinical practice. And I guess one of the things I found interesting, and I guess this might be really elementary and maybe too basic, but the reduction of the mTOR activity through a low caloric diet, intensive physical activity, or pharmaceutical treatment, therefore has general anti-aging effects. That's a quote I pulled. So Here's a question. So maybe in the Western culture, less obesity, you would live longer, and more activity, opposed to dying with a heart attack during a marathon run. Okay, it happens, but
Yeah.
more activity keeps you younger. And
Yeah.
of course, because pharmacists need to make money, if you got pharmaceutical treatments such as cannabis, you might live longer also, or at least age in a body that helps. I mean, one thing about getting older, and this is a quote of my father-in-law, and I love this quote: aging is not for the young. Right? Because
Yes.
it's just not. I mean, because if the young aged quickly, they would be really pissed because it's very gradual, and your knees tell you're getting older. You bust enough ribs on Northgate Trail, your shoulders will start telling you that you're aging. But one thing I've known for a long time as a nurse, as a public health nurse, as a wellness nurse, is that when I'm doing up my laces of my boots, if my belly's in the way, I know it's time to start lowering my intake, right? So like having a body that's easier to function with less, a more balanced diet and more activity, you will age more gracefully. And that's very much an opinionated thing, but it seems to work for me, right?
And that's all true, and that's where the rapamycin comes in.
Yeah.
Is the sort of tricking your body into we'll call it below the neck, thinking you're starving, and above the neck, thinking there's lots of calories, because your brain, and I just try not to go too far afield. I listen to lots of podcasts, and other ones have talked about how in times of stress, either, you don't have enough money, you just got let go of your job, or, literally you're not eating enough. Your brain doesn't make real good decisions. And I'm probably stretching it a little bit here, but if your brain doesn't think that there's lots of food going on, it doesn't seem to do good things for you. So this is just another way of thinking, of sort of making your brain think there's lots of good and plentiful nutrients around, and they found it literally can make more synapses, more connections. So that was really cool. And I kind of, the reason we had a good conversation after I stopped recording is probably because I stopped recording. But Andras went on afterwards about he has actually tried to get this study done in people. And he said, yeah, all it would have taken was, I think it was like 500,000 euros, which call it ballpark $1 million, which, sounds like a lot of money, and is, because neither you or I have that in our back pocket. But in drug trial, that's not a huge amount of money for a drug trial. And yeah, I just kept thinking, because what he was, again, this is all in the maybe, but if you gave someone like a 3 milligram dose of THC, maybe for a few days a month, or maybe a week every quarter, like 4 times a year, what would happen? And, it'd be really easy to administer. And then he was just thinking it could be done. You wouldn't even have to see them, because there's been lots of, especially during the pandemic and even before, it's really easy to administer cognitive tests to people over Zoom. So, you could do the standardized cognitive tests, if you got enough people, maybe you'd only have to do it for a year. Less people, maybe you'd have to do it for 5 years. But, and you have the placebo group, I used, low dose, like 3 milligrams THC a week a month, or a week a quarter, and see how their brains do. And that'd be so cool.
Well, a couple of things to comment on that. Going back to our episodes that we did, episode 115 with Peter Sue, banking on cannabis. We also did an episode with episode 109 with Ryan Cocott, cannabis business attorney. We also did one with David Trailer with the Golden Eagle Partners, episode 110. These are all financiers. So maybe we should turn him on to those guys so he can find the money to do this, because quite frankly, his results go completely against the classic stereotypical stoner. That someone on cannabis is, brain dead, and all they want to do is eat munchies and sit there and watch Netflix all night. But what I find interesting is that the endocannabinoid system keeps us younger with a low dosing, and they're finding that with lots of psychedelics right now. Low dosing mushrooms is helping people with depression. So I can't help but wonder why we can't get funding to do this study, but also to consider our episode 91, dementia and long-term care with Dr. Blake Pearson. He also, helping people in sundowning from dementia with cannabis. You know, we've said this a couple times. It just seems we go through these windows. Early in our podcast, from episode 107 to 114, seemed to be a lot of bankers. The last several episodes seem to be really focusing on the elderly, and I love the fact that. Low dosing cannabis may actually keep me younger and keeping my brain active, like, for example, doing Sudoku or doing crossword puzzles, because they often say that as you get older, and if you do retire, when you retire from your job, one of the most important things to do is to find a hobby, find something of interest, keep your brain occupied, right? So this is all part of that.
Something to occupy your brain. We should crowdfund our own study. All we need is a few $100,000.
Yeah.
And whichever company we partner up with, they can have a certifiable anti-aging pill that people only have to take 3 days a month. Who knows? We'll figure out the exact timing. But yeah, so start sending us wads of money. Kirk and I will run the study. We'll have it on the podcast every step of the way. And whichever company we partner with will have a magic, Reefer Bendis certified anti-aging pill. They should make billions. Everyone should be happy.
Yeah. I'm on that train. Marrakesh Express, off we go. It was another good one. This was a really good study. Obviously, I really believe the study was 2022 though, eh? When was this?
There was two of them. Sorry, I have them here. The original one he wanted to talk about was 2017. That was the making the mice swim one, and then the bidirectional one is 2024.
Okay. All right. So that's why we found him. It was new. It's cool. It's just another study that suggests that maybe, the whole stigma of cannabis, it's like, it is medicine, man. It's medicine and it works and it needs to be studied. And Canada needs to get into more medicinal cannabis studies. And maybe somebody somewhere will listen to this and go, let's call them up and get this study going, because they've been looking for the fountain of youth forever. And wouldn't it be wonderful if the cannabis plant was it?
Yeah, and if you're just because you don't want to be altruistic, if just you're a greedy bastard who wants to make a lot of money by selling the fountain of youth pill, call us up. We'll set you up with Andras. We'll record the proceedings. Everybody will be happy.
Or just grow it in your backyard.
Well, there's that too.
If you were allowed to in Manitoba.
Well, no, sorry, before we do the wrap, it came, not surprisingly, at Country Fest, people, oh yeah, you do that cannabis podcast, yeah. And, talking about the price and too much taxes and not a profit margin. And someone came and said, well, why would anybody, just buy that? They can just grow it in their backyard. And I came up with what I thought was brilliant. So I'll test it out on you. Why not just grow it in your backyard? You absolutely can. How many people grow a tomato in their backyard versus buy it? One buys it because it's easier. It's not to say you can't grow it. You can. Growing tomatoes easy. A lot of people still don't. So, we should definitely have a place to buy it.
Well, certainly. I mean, certainly. And not to get too political, but we should also have a place where we can consume it. But that's, again, go back to episode, 119, 149, when we were talking about, talking with the Manitoba government, that those are issues. When was that episode? Yeah, episode 146. Boy, we've done a lot of episodes there, Trevor.
We've done one or two. Yeah. And this was another good one. I'm Trevor Schufelt. I'm the pharmacist.
I'm Kirk Nyquist. I'm the registered nurse, and we are Reefer Medness, the podcast found at reefermed.ca. We have a very robust webpage. We have a huge cannabis library. You can search it not through the Dewey Decimal System, but actually through drop-down menus. And you can.
No one knows what Dewey Decimal is anymore.
Well, people over 55 plus might. maybe 65. Maybe
right.
65 plus.
And if they took low dose cannabis, they'll remember absolutely the Dewey Decimal System.
Longer, yes, very true, very true. Okay, man, happy Canada Day. We'll talk to you again, I'm sure.
All right, talk to you later.
Cheers.
Okay.